Good afternoon, everyone, and welcome. We are glad to have you all here today. As engineering evolves, it's important not just to adopt new tools, but to maximize the value of the ones you already use. Today's session, Mastering Large Assemblies, essential techniques every SolidWorks user should know, focuses on helping you get more out of your current setup by improving efficiency, streamlining workflows, and enhancing your design process. I'm Rohini from marketing team at EGS India, and I'll be your host for today. Before we begin, all participants are muted. For better connectivity, feel free to drop your questions in the chat anytime. We will address them during the question and answer session at the end of the presentation. At EGS India, we believe strong design engineering drives innovation. Often, many features within SolidWorks go underutilized. Making better use of it using existing tools, you can reduce rework, save time, and improve overall productivity. Now it is my pleasure to introduce our speaker, Mr. Anish Kant. He's an application engineer at EGS India, a SolidWorks value-added reseller with expertise in Dassault system software across multiple industries. With over 20 certification in SolidWorks and Dassault system software, he is dedicated to helping clients to get the most out of their tools.
Thank you. Good afternoon, everyone. I think we can start with the presentation today. So first, we'll look at the agenda for today. First, you're going to understand what happens when you open a large assembly. So the topic is basically on how to optimize a large assembly file, on what are the processes that you're going to follow to make the effort and time reduce. So the first, we're going to understand what happens when we open a file, when we open a large assembly, what is happening. And next, we're going to look at what are the issues that we face generally, common issues that we face with large assemblies. And then we look at the steps which will help us reduce the time and effort put into a large assembly when we're opening, updating, rebuilding, and finally working with the file. And we'll conclude with the findings. Before we start with the presentation, I'll just introduce to who we are in EGS India. So we are a team of around 140 people in around 3 locations, Coimbatore, Chennai, and Trichy, with our headquarters at Chennai. We have a presence in around 1,500 customers. We are also affiliated with chapters such as SAE India, IMT, ME, IPI, etc., with annual growth, year-on-year growth in the last 10 years. So what we do, we are mainly into 3 different branches. One is the engineering services, where we do services on design validation, FE, etc. Another is going to be your technology training, where we train people with respect to GD&T, tolerance tags, FMEA, DFM, etc. And the division that I'm from, Software Solutions, we deal with mainly Dassault system products, where we resell and support SolidWorks and other softwares within the same solution. I think we can start with the topic for today. So what happens when you actually open an assembly file or a drawing file? So first, your assembly is going to be in your disk or storage, where we first load all of the files back into the RAM. When you open a file in SolidWorks, it is not just a single step process in the first place. It is first read from the storage and then loaded into the RAM for access. The processor mainly handles all of the calculations and rebuilds the model, basically calculates what is supposed to be put on the screen. And the GPU helps you convert all of this digital data into a visual output. So all of these 4 components are going to be very essential for assembly file to open. So the first is going to be where the assembly is stored. The next is going to be what transfers it or does the calculations and brings up with the model. Your RAM is where you're going to be accessing the model from. And your GPU is what is going to convert the information into a digital model. So this is for a single file. Now, what happens when it's a large assembly? So the entire same process where your file gets called from the storage, it gets loaded into your RAM, your SolidWorks/processor works on the data, and your GPU produces a graphical representation of it. So all of this process is going to take is going to be multiplied for every single file or reference. And keep in mind, it's not just the number of components within your assembly, it is also the components that are referred by your assembly. So a number might be different in each case. For a large assembly, it might be 2000 components, it might be 5000 components. But what is important is that this process which goes on will be multiplied with as many number of components as it is there. So the main important factor is inevitably it takes time, it takes resources. What do you mean by resources? So like I said, the same components such as the processor, RAM, and GPU, that is what we're going to be calling as components and resources for today. The first one is going to be the processor. So what it does is the processor is the one that deals with the data. So the component that does all the calculations to read a file, open it, and produce the information needed for the GPU is done by the processor. It is responsible for reading the file and understanding what the model consists of. So basically, every feature or part that you build within SolidWorks is going to be calculated, and output is going to be given by the processor in the first place. So what is your normal workflow when you work with design or CAD in SolidWorks? So first, let's say that you're going to create a simple part file over here. What you first do is you first select a plane. So that is what we first do. First, we define or select a plane. And with the plane, we're going to create a sketch. So with the reference of a plane, we create a sketch. With the reference of a sketch, we're going to build the 3D geometry, which is built by a feature. So over here, we showed a simple extrusion. And the body is then modified with respect, with the help of other features such as fillet, chamfer, cut hole, etc. But the point that I'm trying to make over here is this design process is a sequential process. It's a step-by-step process where we need the plane to define a sketch. We need the sketch to define an extrusion, and the extrusion is needed to define a fillet. And the same process of plane to sketch to extrusion to fillet is going to be carried on by a processor as well. So what I'm trying to say is each step needs information from the previous step, which means it is going to be it is not possible to multitask within this simple operation over here. So this is why we say when SolidWorks, it is a step-by-step process where the speed of the core matter than the number of the cores. So usually we might have different processes within the same league, which say that this has a better speed, this has a more number of cores. But with SolidWorks, we are more focused towards the speed of a single core rather than the number of cores. Like I said, the CAD process within SolidWorks is a sequential process where we need to complete the task step by step. Similarly, when we go to the RAM is going to be a temporary workspace where SolidWorks is going to work on. So it is in a very simple way. When you open a file in SolidWorks, the file is first taken from your hard disk and loaded into your RAM. So you're not working on the file directly from the disk, but on a live copy inside the RAM. So now every change that you make, editing a sketch or changing a dimension or moving a component, all of that is first going to be temporarily stored within the RAM only. So these are the changes that are meant in the RAM. And when we press Control S or when we press save, that is when it is stored onto the disk. So what I mean to say is any change or anything that you do within the SolidWorks environment is going to be saved within the RAM and not towards the disk directly. So when you're working with large assemblies, all the component data needs to be loaded onto the RAM. So if you're having 2,500 components or 5,000 components, all of these components need to be within the RAM in the first place, and that is when we work on it. So when RAM doesn't have enough space, it creates a bottleneck. So what I mean by bottleneck is a sudden drop in performance or speed. So that usually happens when you don't have enough RAM capacity in your system. So the best approach for us is to monitor your usage and upgrade based on your actual requirement. So let's say, depending on the assemblies you work on, depending on the components that you have, you can decide which amount of RAM or what amount of RAM is needed for your assembly over here. So next hardware consideration is going to be the GPU. So like I said, the GPU takes information from the RAM and processor, and it is responsible for displaying it on the screen. So it controls how smoothly you can rotate, zoom, and work on the models. For the best results, SolidWorks recommends certified graphics cards, as gaming GPUs are not officially supported. So the most important thing is SolidWorks does have a certified set of graphics card in the website, which they suggest or prefer when it comes to large assemblies in SolidWorks. Also, using the correct and tested driver version is also important, since the compatibility between your system and your graphics driver is going to be decided with the driver only. So a newest version of driver is also recommended. So as a summary, for all these hardware considerations, it is going to be first prioritize higher clock speed over core count. So the number of cores do not matter for a CPU, but rather the fastest clock speed is what is required for SolidWorks. So next is going to be a higher RAM requirements when working with large assembly. So the basic requirements might only be 16 GB RAM, but when you're working with large assemblies, depending on your usage, we might have to increase the RAM to the next level. And the third hardware consideration is going to be your certified GPU with proper supported drivers. So this is all it is going to be for the hardware considerations. We can now move on to SolidWorks. So now that we've covered the hardware requirements and recommendations, let's shift our focus to SolidWorks. Before jumping into solutions, we'll look at the common issues that usually come up with large assemblies. So usually we'll have customers complaining that it is taking a lot of time to open. It has even a small change is taking a lot of time to rebuild. Even rotating a component is leads to SolidWorks freezing up. Mates taking a lot of time to solve. That is issues when you're working with main big assemblies, etc. So these are the common issues that we heard when it comes to large assemblies. So for explaining this topic or explaining this vast number of opportunities for you, we're gonna first filter it out into three categories. So what are the three categories? So I'm going to classify these issues into three categories, such as one, issues when you're opening a file. So let's say that the assembly is taking a lot of time to open, or assembly is getting stuck when it's trying to open, or SolidWorks closes when it's trying to open, etc. Next category is going to be when it's updating or rebuilding. So let's say you make a small design change or change a small dimension, create a new mate, etc. But the assembly takes too long to respond. So that is going to be the second part. Third part is when you're working or editing the assembly. In the sense, if you're rotating to view more components, zooming in, zooming out, issues when usually happen when you don't have any features or editing going on, but rather just changing the orientation of the assembly, etc. So it is important to understand that all of these are interconnected. So the suggestions that I'm about to make or recommendations that I'm about to make, it is common for all three issues. It is not just going to be only for opening or only for updating or only for the graphical issues, but improving one area can positively affect the others, giving you overall better performance. So I think let's see how this can be changed now. So the first point from the first category where it's going to be about opening is storage location. So with bigger firms, with a lot of people in the design team, let's say there is a team of designers, it is common to see a network drive or a server setup where the files are hosted directly at the server and are accessed by the systems or client systems. So what happens when we open over a network is that the data is not sent in one piece. So let's say you're opening an assembly, the entire assembly is not going to get loaded into your RAM in one go. What is going to happen is the data is going to be split into smaller pockets, file by file, and it's going to come to your RAM. And the problem with the network drive is, for each packet sent, the system is going to check if the connection is okay or not, if the file is okay or not. So these are called the handshakes between a system and a server. So all of this consideration makes it hard for SolidWorks to open a large assembly with n number of references directly into your RAM. So this is the first major factor. Second major factor, let's say there are 5 people working in a small server setup, where everybody is still trying to access a large assembly file. So the server system cannot allocate all the resources directly to one person, meaning the traffic is going to slow it down. So the rate at which the small packets of data is going to send is going to be split across all users, making the entire process slower for all 5 people. And next, since there is a lot of files going in and out of the server, there's definitely got to be an antivirus system which scans the files before sending it to your RAM. So even that takes up a lot of time, where it has to go through all the packets sent and then load it onto your RAM and open it in your Solidworks assembly. This is why we say always work with a local drive. So files are opened instantly. There is no handshakes required or there is no external connection required. So it is inevitably going to be faster. So I do have proof to show this to you. So we've got the same assembly over here where it is one version of it is hosted in the network drive, and the same file is again hosted in your local drive. You can see over here that I've recorded the timings for both the files. If you do fast forward and look at it, you can see that the network drive takes nearly 1 minute to open the files, but the local drive is going to cut it down to 30 seconds or nearly 35 seconds. And I assure you, this is with the default system settings without any other optimizations. The only change between both these files is going to be the storage location. As you can see here, the opening time drops to almost 50% when the assembly is saved locally, a significant time where there are no modifications done. So another benefit to working locally is there is a lot of problems which can be prevented, such as references missing or file corruption. So overall, it gives a faster, smoother, and more reliable experience, especially for the large files. What do I mean by missing references or file references? So if you look at it over here, so every assembly, it is going to refer n number of components. So it can be its own sub-assemblies and its own parts inserted within the assembly, or it can be files that are referenced by those sub-assemblies and part files. So when SolidWorks cannot find the particular file, it goes on to a search. So this is the order of search which usually happens. So first it's going to be the RAM, where it tries to find the same file within the open documents which are currently open. Then it goes on to a specified location that you mentioned under the reference document. And then it goes on to the path used by the assembly. So if it is stored under the specific folder within the assembly, it goes in search of within the folder and then the previous folder, and it goes on a circular loop. So when the locations are not proper, when you don't store your assemblies within the same location, everything, the time taken for it to search all the folders and go through the entire search order and then come up with your file is a lot. So for a particular file, for 1 or 2 files, it may only be in small, very minute amount of time. But when it multiplies across 5,000 odd components, then the difference in time is astonishing. So to reduce that, we prefer to have all the assembly and files within the same location, or at least within the same folder. The next is going to be your file version. So when you're recently upgraded to SolidWorks version, or if you've moved from a previous version to a newer version, you can see that when you're trying to save an old file, it shows a pop-up saying, saving this will convert the following files to the current version. So what usually happens? It doesn't just directly load it to SolidWorks, but since there is going to be a difference in the version, this involves rebuilding the model and reevaluating geometry every single time. So once the file is saved in the latest version, this extra step of reevaluating geometry and rebuilding the model is not needed. So even for the same assembly that we looked at over there, you can see that around 176 files, as it shows, is not in the current version. So updating it to the current version would help in reducing time. So next, often with large assemblies, we also handle common neutral files which come up in the form of step. So when you're importing step file, or let's say IGS file or any other neutral format, Solidworks usually maintains a link to the original file, and this is done with the help of this concept called 3D interconnect. So what usually happens is when you're opening a step file within SolidWorks, the step file is not directly converted into a SolidWorks file, but rather a link between a SolidWorks file and the step file in itself. But what this means is every time the model is open, SolidWorks will usually check whether the source file has changed. So it'll basically try to re-elevate the link between the step file and your SolidWorks file over here. So it also creates a dependency on the file location. So especially if the file is stored on a network or something, it'll again go find the step file, try to re-update the link, and come over here. So that is why we all often suggest the break link over here. What break link does is it breaks the link between the step file and the SolidWorks file and converts it into a SolidWorks file in itself. So by doing this, the first time that you create an assembly file or you use the components, the next time that you open an assembly or the times that you open the work on the assembly after that, it helps. So once you're done with the neutral file format, when you're opening an assembly, you have three opening modes. So one is called the resolved mode, that is the default mode that it opens in, the lightweight and the large design review. So I'll just show you an example over here where we open the file with the large design review. You can see that the assembly opened within 5 to 6 seconds. So why is that? So the difference between the three opening modes is that SolidWorks lets you choose what level of data or detail you want with it when you're working with the assembly. If you want to work on just the exterior or you want to create a structure system for this assembly, then you don't need the details within the assembly or uh, the data or model geometric data of the parts within the assembly. But let's say that you want to make edits on the assembly itself, then you will have to go, then you'll be needing the geometrical data. So depending on the uses or the requirement that you have of the task, you can choose the opening mode over here. This one is opened with the help of the large design review mode. Where you can see that it only has certain capabilities such as which are mostly required to reviewing the assembly. So you can just go through the, you can measure different distances between components, you can check for interferences, you can create cross sections and see within the component. But without the edit assembly option enabled, you will not be able to insert or delete components or move and rotate components, etc. So what it basically means is you don't have to load the entire assembly every time you just want to look at it. So this saves significant amount of time once the design is completed when it goes for review or when you just want to make sure that the changes have been updated. You don't have to you don't need to load all the data within your SolidWorks system. So when you're opening an assembly, you can also see that there is a open indicator. For most of the people, I think they would have ticked the do not show again and closed it off. But again, so what this open indicator does is it helps us identify in what phase the delay is happening. Is it happening when the files are getting loaded onto the assembly, or is it happening when it's updating the assembly, or is it getting slow when it's updating the graphics? By closely observing the opening status, we can understand what is happening behind the scenes. So it gives us clarity on where time is being spent and which part of the process is slowing things down. With this, we're going to conclude the category 1 of it, where we looked at options or features which have helped in reducing the opening time of an assembly. The next is going to be your rebuild time or update time. So when you make changes in the model, SolidWorks needs to rebuild it to update all the dependent features. So the most models are built using a chain of features where each one depends on the previous one. So a small change in the beginning can affect everything that comes after it, increasing the rebuild time. And let's say that we have paths that refer other files or paths that refer other subassemblies, then the external references add another layer. So the amount of time required to go through rebuild and calculate all of these steps in between is going to be a lot for a large assembly. So we'll look at how it is going to be, you'll be able to reduce it in the future time. The first option in that is going to be the in-context features. So when you're trying to create a top-down assembly or when you're trying to refer existing components and create geometry, for example, let's say that you're creating a build plate for an existing member, a base plate for an existing member, then we'll need to know the location of the existing member so that you can create a respective base plate. But over here, you can see there's an option called no external references. So this prevents the creation of external references when you create or edit features in the assembly over here. So this is very useful for design intent as it creates dependencies between parts. So when one component changes, all the related components may also need to change or rebuild. And the downside to it is that it increases overall rebuild time and makes large assemblies slower and more complex to manage. Since features are going to be depending on an existing geometry, it has to calculate um, the dependencies first and then rebuild your model over here. So the same concept applies for the next topic where we prefer to reduce the top level mates. So what we mean by top level mates is when you have layers of an assembly. Let's say that you have a top level assembly which contains sub assemblies within it. We prefer not to maintain your mates in the top level. So what I mean by the top level is for all the mates that are going to be rigid or do not move, we prefer if those are within the sub-assemblies itself and framed as rigid components. So when you do that, the calculations or the dependencies are going to be calculated easier since the top level is free. And since the sub-assemblies are going to be rigid, the mates within the sub-assembly do not have to be rebuilt every time or do not have to be reevaluated every time. But in the case where we apply all the mates in the top level assembly only, every single mate applied will have to be reevaluated and rebuilt, irrespective of the change or its status in the assembly. So this is we prefer to have the mates within the sub-assemblies as much as possible. This does have some restrictions when it comes to checking movement or moving the parts. So depending on the usage and depending on the context of your assembly, this can be used. So the next topic is going to be pattern or mirror references. So what is going to happen is we have a component which we have patterned as a linear pattern or circular pattern, etc. And new components are going to be mated to the patterned instances. So the dependency is built in such a way that we first have a geometry. There's going to be a pattern built on the geometry, and then there's going to be made to the built component. So to reduce this dependency link, we are going to suggest patterning directly to the parent assembly or directly to the parent planes or references as such, and avoid mating it to the patterned or mirrored components. So to reduce the amount of complex mates over here, this is why we refer to this. The next is going to be for avoiding equations at the top level. So similar to the previous two topics where we reduce the complexity of the assembly, this is another concept which would increase the complexity of the assembly. So the top level assembly equations control multiple components and are evaluated during every rebuild. This creates a global dependency across the entire assembly. So even the sub-assemblies or components which refer the top assembly are going to be affected by this. So this creates a very big dependency link, which is going to take a lot of time to rebuild and reevaluate. And the final topic is the automatic rebuild. So what do you mean by automatic rebuild is for every single change that you do within the assembly, let's say that you change an extrusion from 10 to 20 that small change is going to trigger an entire rebuild for the entire assembly. You might not be done with your changes. There's going to be 2 or 3 more changes that are yet to be done, which are caused by this first change. But SolidWorks by default is going to send an entire rebuild, and this is going to affect the existing geometry also. So in large assemblies, the automatic rebuild can actually slow your workflow down, as even the smallest change will lead to frequent delays. By turning off this automatic rebuild, we can make multiple changes at once and rebuild only when necessary. So this gives better control and improves the overall working speed. So the time spent in rebuilding the assembly is going to be reduced by this. And this is the most important topic, where performance evaluation. So with this set of features and with this set of suggestions that we've made, we can now check what other steps can be followed with this performance evaluation. So you can analyze the assembly performance in detail. It identifies which components take a lot of time to load, which takes a lot of time to open. It also shows which feature in particular takes a lot of time to rebuild, etc. So this tool helps us to understand where time is actually being lost in the assembly. So it identifies components, features, and mates which take longer to rebuild. This allows us to focus on the areas that have the most impact on performance. So you can figure out which component or which feature is taking the most amount of time, and simplifying that can give you a significant time saving when you look at the overall assembly over here. With this, we can again go to the category 3, where it is mostly going to be about your graphical data present in the model. So what do you mean by the graphical data? Like I said, the processor is going to give the GPU information on what is going to be displayed in the assembly, and the GPU is going to calculate it and present it in a visual form in front of you. But how does it get transferred to your display over here? So that is the concept of graphical triangles over here. All the cylindrical faces or spherical faces or curved faces is going to be broken down into straight lines. So the smaller the straight lines, the more number of triangles, the more detail that the assembly or the part is going to have. But the problem is with this is the number of triangles increase, it also takes a huge toll on your performance over here. So if you see over here, for a small cube, irrespective of the amount of detail, the overall graphic triangles is going to be just 12 graphic triangles. But if you take a sphere, depending on the image quality, your cylindrical faces is going to be split, meaning changes in the image quality is going to affect spherical faces more than your flat faces over here. So if you're only going to be working with weldments where there is not going to be much spherical spaces, then image quality might not have a huge impact for your file. But if you're somebody who is working with surfaces and a lot of curved parts, then this is going to be a very important topic for you. So by reducing the image quality in one level, in one way, is going to reduce the amount of graphic triangles from, in this case, the sphere, from 9,000 to 600. So this significant change does not cause any loss in data or anything, but just the representation on your system. So if we see here on the left side, both the cylinders, it is the definition of the cylinder is going to be the same and the geometry is going to be the same. But how it is represented on your screen is going to be different over here. And this is about the graphic triangle over here. In some another point to note is that in some cases, even covering the complex geometry will help you in reducing the number of graphic triangles present. So the next topic is going to be about the option that is going to take up a lot of graphical data. So if you see over here, the first option is the real view option, and the second one is the shadows option. So both of us is going to be there in your viewport, where both these options, while it makes the appearance look better or it makes the design look better on SolidWorks, it is going to take up a lot of graphical resources. So when working with large assemblies, we recommend turning it off, as these options can significantly improve your smoothness and time taken in updating the graphics. So next is going to be with respect to your appearances. So as you see over here, in an assembly, appearance can be given for a face, a feature, the entire body, a part file, or the assembly file in total. The higher level appearances always overrides the lower level ones. So what I mean by that is, any appearance given in the assembly level is going to override the one in part level. Anything given in the part level is going to override the body level. Anything in the body level is going to override the feature level, and anything in the feature level is going to override the face level. So instead of applying the same appearance in the face, the same appearance in feature, the same appearance in body, you can directly go forward and give the appearance in the part or assembly file. So this is going to save a lot of time and effort by the system or the resources required, as these multiple overrides can increase graphics processing and also make it difficult to understand why the model looks a certain way. Let's say there's some issue that needs to be sorted or anything. It needs to be troubleshooted. Then it is easier to do it when it is applied at the higher levels. So this is the suggestions that we make towards the appearance or the hierarchy of appearances, where with respect to your requirements, the highest level is more preferred rather than the faces or bodies. So the next topic is going to be between display states and configuration. So for someone who's well-versed in SolidWorks, I think they'll know the difference between display states and configurations. But I'll just give you a small explanation of what it is. Configuration is going to be a tool or a way where you can store multiple variations of your design within a single file. So instead of creating multiple files with different small variations, small dimensional changes, you can all maintain it with respect to within one file itself. And display states is the same for graphical data. So instead of changing the design itself, we are only going to be changing the cosmetics or the colors of it. So that is the difference between display states and configurations. While the display states are while the configurations are very helpful when you are controlling geometry or features, for when we only want to see how it looks in different colors, or you only want to control the visual aspects like appearance and visibility, you do not require to rebuild or reload the entire graphical data. Model data. So that is why we prefer, for any change that is to be done only cosmetically, always go for display states rather than creating new configurations. So within the same configuration, you can create multiple display states to show different types of cosmetic changes. So this is the recommendation when it comes to appearances. The next is going to be a topic called speed pack configuration. So a speed pack configuration helps improve performance by loading only the essential faces and bodies required for the assembly. So this is again a subtopic of the configuration part, where we can create a speed pack configuration, where we can select what components to load as graphical data and what components to load as geometrical data. So let's say that I have a huge assembly where where my current task is only going to be creating a base for it or creating a structure system for it. So at the time, I don't need the components, or I don't need the data, which are going to be the internal components, internal workings, internal parts. This is not going to be needed. So at that time, I can create a speed pack configuration which has only the main support members and main structural members visible for me, selectable for me, and the remaining data need not be loaded onto the SolidWorks environment over here. So again, with respect to the task at hand, this can be deployed over here. In this example, you can see that there is a ghost circle seen where when the cursor is over the parts. So this is because the entire subassembly has been converted into a speed pack over here. When using the speed pack configuration, the structure system or other components, this data is similar to an image. So basically, just a graphical representation and not the model data entirely. So while the speed pack offers great performance benefits, it also requires proper understanding to use it effectively. So when creating the speed pack, we need to be sure on what components you need the graphical data on what components you need the geometrical data on. So once we have that defined with proper procedure, you can create a speed pack configuration and deploy it across other sub-assemblies or main assemblies over here. So the main concept or the main topic which concludes all three categories is going to be the large assembly settings. So the large assembly settings is just a single button that you see in your command manager, but it is a compilation of all the options that are required to work better in your large assembly. So the same can be applied with respect to your system options itself, but this is just a compilation of all the settings together or a temporary settings, which makes follow changes in the drawing options, display styles, it makes changes in the performance options and view toolbar options. So we always recommend having this on when working on large assemblies, since you don't need to specifically go in search of options that will make your performance better. This is a compilation of it, and another benefit is that it's temporary. So within a click of the button, all of that can be resetted back to its default settings over here. And this is another example of that simplification that I told you about. You can see here that I've got a small spring-like feature over here, where in one version I've covered it with a small extrusion. The other one, it has the spherical surface on it. So you can see over here that the graphical count, it's very small, I'm sorry about that, but the graphic line count has reduced from 25,000 to 2,300. So almost 1/10 of it. So the resources required for rebuilding or generating this part is also going to be 1/10 of it. This is mainly used for standard components such as nuts and bolts. We're not going to be creating a detailed view of it. We're not going to be detailing the component since it's a standard component. So in this case, we only need a representation of it rather than the entire model. In some cases where we're working with standard components, we might need the exact data or the exact thread or the feature available so that you can check the interferences and etc. So for that, we recommend converting it into a separate configuration. So rather than changing the entire geometry in itself, you can create a configuration where it is simplified. So when we're working on other components or other parts of the subassembly, you can work with the simplified configuration, whereas the exact geometry is going to be for the when you need the detail. So basically, the data is not lost over here, but it is just going to be hidden for your current feature over here. So with this, I think we can conclude the topic over here. So what we've basically done is to handle large assemblies. Efficiency is not just about having better hardware, but about how we manage our structure data. By identifying where this issue occurs and whether it's during opening, rebuilding, or working, you can apply the right optimizations. And with simple practices like reducing unnecessary detail, controlling dependencies, and using the right tools can make a significant difference. Implement these techniques in your daily workflow and create standardized practices for large assembly handling across your team. Measure, optimize, standardize. Thank you.